Hello, everyone. My name is Anna Mutala, and I'm a professor at Riga Technical University. But here today, I'm representing not the Riga Technical University, but European Union Horizon project called SMOPO. And the project is related to the energy system modeling. And actually, it was the kind of basement to create this course and to integrate this tool into this course and make you maybe a bit to provide you some introduction to the energy system modeling and how the how the open tools can be used for this. I also would like to notice that to say that VTT is a Finnish research institute, which is one of the leading research institutes in Europe, is coordinating this project. That's why we are in Finland. I mean, you are in Finland, but I of course still be in Latvian Riga. But yeah, so they are coordinating this project, and it was an initiative from their side to create a specific course for the students. However, I also need to mention here that the project itself and actually the tool itself, it was developed, and the idea to develop this tool was for the particular stakeholders, which is the transmission system operators and the policymakers. But we always, when we are developing some open tools and we are working like open science, we consider also university students, and we are also trying to involve them in the community. And in this case, this is a very huge and interesting energy system modeling community. I need to say also big thanks because this this let's say block of 3 lectures was developed, as I said, under the MOPA project, but with participating of RTU team and VTT team. I need to say big thanks to my colleagues Carles Balputnes and Zana Broka, particularly developing this presentation, helping me to develop this presentation to prepare for you. And I also would like to say big thanks, and you will see them later on, specifically Yasuinas, who will be providing the assignments for you, not as like tasks related to the tool. And I also, of course, would like to express my gratitude to the Professor Henrik Tolvanen for his significant contributions in the development of this course. The course consists of 12 lectures, and so I'm responsible only for 3, so the other remains on the Henrik. And thank you very much, Henrik, for this opportunity. Okay, I will maybe switch my video for the better quality. And if we're talking, I already presented the kind of scope and what we are going to do. It will be related to the open tool. We will have a block of 3 lectures where we will explore the modeling, how to model energy system. I know that earlier you get familiar with the modeling energy consumption and various types of generation. You also gain some knowledge on how energy systems are designed. And in general, we need to summarize this knowledge and frame it to the approach how to model big energy systems. In this lecture, I will introduce the key concept and tools used in the energy system modeling, and I will start with the overview of the different types of energy system models and the various modeling tools available as well. And this will be followed by a lecture on the spine op tool, the tool we will be using. And it will be, the lecture is already prepared by my colleague, and we have a video recording. Yes, so let's go into maybe more details, and the choice of energy system models primarily depends on the specific task we aim to solve. Each task is associated with a particular group stakeholders, such as researchers, policymakers, or industry professionals. Since these stakeholders have different objectives, they require models they can analyze various scenarios and support informed decision making regarding energy generation, distribution, power system development, and so on. If we are talking about energy system models, they definitely need to be classified to make them use in a more easier way. And there is some classification by methodology. This includes top-down and bottom-up approaches, input-output models, simulation-based models, and optimization frameworks, each serving different analytical needs from broad economic assessment to detailed technological analysis. By purpose, models can be designed for forecasting, for policy evaluation, depending on the intended application. By sectoral coverage, models can focus on the specific sector, such as electricity or, for instance, transport, or be integrated like multi-sectoral models that capture interdependencies between energy, economy, and the environmental. Another direction is by resolution and level of details. This classification considers the time horizon, which could be short, medium, or long term, time resolution, low, medium, or high, spatial or geographical coverage, single region or multi-region models. Most likely you already know there is classification of the geographical regions exist, and it was developed for the statistical analysis, and probably you are familiar with some kind of like a NUTS 1, NUTS 2, and for instance NUTS 1, it's a classification related to the country. NUTS 2, it depends on the country. For instance, we are talking about the Latvia, my country, so NUTS 2, it's also related to the country level. If we are talking about neighboring country, which is Lithuania, the NUTS 2, it's already, the Lithuania is already divided by the regions. So it's also important for the energy system modeling. Another classification is by programming technique and mathematical logic. Models may use linear or non-linear optimization, deterministic or stochastic methods, and various levels of mathematical complexity depending on the problems they aim to solve. If we are talking about modeling methodologies, I can maybe emphasize like maybe two main, but at the same time maybe I need to mention here four methodologies, which we'll call like a primary. One of them, optimization model, use mathematical techniques to find the best solution under given constraints, such minimizing costs, maximizing efficiency, or for instance, it could be also reducing of emissions. Those models are widely used for the system planning and operational scheduling. Simulation models focus on reproducing real world system behavior and are widely used for forecasting, policy analysis, and assessing market dynamics. You may be familiar with the digital twin concept, but now simulation twin are emerging. So we are like kind of shifting from the digital twins to simulation twins because they are more addressing like a precise representation of the energy system modeling. Another methodology, it's an econometric model which applies statistical and economic behavior to analyze historical energy data and predict future trends. This methodology helps assess the relationships between energy supply, demand, and pricing, often used in the market and policy studies. The other models mentioned here, more or less hybrid. Probably also I need to mention here or emphasize the methodology which is user-friendly. This is a spreadsheet model which is used softwares like, for instance, Excel, which is very well known. It also can be used to simulate energy system behavior, even under various constraints. But definitely this methodology lacks scalability for the complex and large-scale system. And some other known, some of them very well known, some of them maybe less, but other methodologies also exist, like a Markov chain, like an integrated assessment model, which actually combine energy, climate, land use, and economic models to analyze interconnection between energy and broader social challenges. Also, geospatial models, which actually integrate geographical information system data to assess spatial distribution of energy resources, infrastructure, and demand. Depends on the goal of the modeling. So simulation models may include optimization elements. Optimization models can incorporate geospatial data. Understanding those methodologies help in choosing the right tool for the different energy system challenges. And of course, we can also say that most of the open access tools use hybrid approach. So it means the combination of the different tools for the different tasks, kind of data preparation or optimization techniques and so on. If we look at the energy system modeling from the purpose perspective, then optimization models are typically used to explore a range of scenarios. Their purpose is to present possible system evolution with estimating likelihood. Those models can also take a normative approach, meaning they define systems that can only be achieved through specific actions, essentially seeking a target state. On the other hand, simulation models are commonly applied in forecasting. Their role is primarily predictive, aiming to represent how the system behave under given conditions. The table you see on the slide categorize different energy scenario approaches into three main groups. Explorative scenarios explore what may happen by analyzing multiple possible features. Normative scenarios define what future we want, focusing on desirable outcome and gaps to be bridged. And predictive scenarios estimate what future we expect, including a range from best case to worst case outcomes. Key questions to ask when choosing the modeling purpose is Does the model provide a snapshot of the system, or does it define a pathway or evolution? Uh, re- uh, Returning to the methodological approach, two primary modeling frameworks can be used. The top-down modeling and bottom-up modeling. Each has distinct characteristics and it's suited to different applications. Top-down modeling takes higher level perspective, focusing on the overall energy system. It relies on the aggregated data and historical trends to make projections about total energy consumption. For instance, gas usage for produced electricity. This approach is particularly used for the long-term planning and policy analysis, as it simplifies complex energy dynamics into broader trends. On the other hand, bottom-up modeling starts from a more detailed perspective, analyzing individual components and processes. It provides a higher level of granularity and understanding, it making it more suitable for evaluating specific technologies or conducting local assessments. This approach considers detailed factors such as a heating system, for instance, air conditioning, lighting, to provide precise energy demand estimations. The choice between top-down and bottom-up modeling depends on the objective of the study as well. Another reported factor is the sectoral scope. An energy system interacts across multiple domains. This diagram illustrates how different energy scenarios are integrated and interconnected with economic and climatic factors. At the core of the system is the integrated energy system, which links power, heat, and gas system. Those subsystems interact to balance energy demand and supply across different sectors. Energy consumption and generation are influenced by various end user sectors, including industry, including transport, buildings, also separate, could be like a hydro circle and renewable resources such as the wind or solar. Each sector has specific processes and dynamic, such as industrial processes, transport mobility, and the hydrological cycle for instance, hydropower. This approach highlights the importance of cross-sectoral modeling to achieve a holistic understanding of the energy system and improve decision-making for sustainable energy transition. So it is important to cover various sectors in the energy modeling. In the in an integrated energy system, the key challenges is to continuously balance supply and demand in real time. This requires a coordinated approach across multiple energy sectors, infrastructure, and consumption sectors. A critical aspect of this process is the cost-optimal dispatch of the generation units. This involves making strategic decision on the optimal use of energy storage, interconnectors, and demand response mechanisms. While considering technical constraints, market condition, and regulatory framework. Additionally, the planning of the energy system focuses on identifying optimal investment strategies under uncertain future conditions. With increasing system complexity and sectoral independencies, interdependencies, it becomes essential to spontaneously consider multiple energy sectors, ensuring efficient operation and long-term sustainability. By integrating different energy carriers, such as electricity, heat, gas, allows, along with the various generation technique, storage solution, demand side measures, and optimization model enable decision makers to develop resilient, cost-effective, and sustainable energy system. Energy system models can vary significantly in their resolution, depending on the level of details they aim. This slide highlights the key aspects of resolution in time, in space, in technical economic details, and sector coupling. First, time resolution can change from sub-hourly intervals for real-time operation and the flexibility analysis to annual time step for long-term energy planning. Next, spatial resolution can span from individual power plants to continental scale models. More detailed spatial resolution help capture transmission constraints, region variations in resources, in infrastructure dependencies. The level of the techno-economical details also varies. Simpler models may use linear aggregation to represent power plants, while more advanced models incorporate dynamic startup cost, efficiency variation, and storage interaction. High resolution in the domain improves the accuracy of economic and technical feasibility assessment. And finally, sector coupling determines how different energy carriers, such again electricity, gas, heat, industry, and transport are integrated. Models with a low sectoral resolution may only consider, for instance, electricity, while high-resolution models capture the interaction between sectors. The appropriate choice of resolution depends on the modeling objective, balancing computational complexity with the level of detail needed for decision making. When designing energy system models, there is always a trade-off between resolution and computational time. This slide illustrates how different modeling approaches balance spatial coverage, level of details, and computational complexity. On the horizontal axis, we see an increasing level of details, ranging from simpler models with constant efficiencies to more complex model incorporating part load efficiencies and additional system features. At the most detailed end, white box models provide high resolution system representation but require significantly more computational resources. On the vectoral axis, spatial coverage expands from small-scale models focused on individual buildings, for instance, or distinct to large system models covering entire transmission network. The higher the spatial coverage, the more data-intensive the model becomes. The type of optimization problem also influence complexity. Linear programming models are computationally efficient but may lack details. Mixed integer linear programming introduce additional constraints such as the unit commitment decision. It also increase computational requirements. Mixed integer nonlinear programming provides the highest levels of details, capturing also dynamic system behavior, but in a high computational cost. The arrow representing computational time highlights that we increase both spatial and coverage and detail. Computational time grows significantly. Therefore, the models must be balanced between accuracy and feasibility, choosing the appropriate level of complexity based on the research question and available computational resources. In energy system modeling and optimization, different mathematical programming techniques are used to solve complex problems. This slide categorizes optimization models into continuous and discrete approaches. At the top level, optimization can be divided into two main branches: continuous optimization, where variables can take any real number of values, and discrete optimization, where some or all variables must take integer values. Continuous optimization includes linear programming, quadratic programming, which extend linear programming with the quadratic objective function, nonlinear programming. Discrete optimization includes integer programming, where decision variables are restricted to integers, mixed integer linear programming, which combines linear equations with both integer and real number variables. Mixed integer nonlinear programming, allowing nonlinear relationships between variables. The table on the slide summarizes key characteristics of each method, including the objective function type, linear or nonlinear constraint characteristics, and decision variable types. Choosing the right optimization method depends on the problem. Linear programming and mixed integer linear programming are widely used for the energy market and operational scheduling, while nonlinear programming and mixed integer nonlinear programming are essential for detailed technique modeling of the energy system. But if we're talking about the open access tools, so some they already use some of these optimization techniques, and or maybe a combination of optimization techniques. When modeling energy system, we also often distinguish between deterministic and stochastic approaches, depending on how uncertainty is handled in the system. A deterministic model assumes that all inputs are known with certainty, and the model produces a single predictable output. As shown on the graph on the left, this one, deterministic model generates one trajectory over time, representing a fixed and reliable outcome. The diagram on the right for the deterministic method illustrates how a deterministic system takes inputs and processes them through functions, resulting in the well-defined output. In contrast, a stochastic model incorporates uncertainty and variability in its input, leading to multiple possible outcomes. In the graph on the left, instead of the single trajectory, we see multiple possible future paths, in this graph, and reflecting uncertainty in prediction. The model diagram on the right shows that input variables in stochastic models can follow probability distributions. What is the key difference and application? A deterministic model are often used when system parameters are well defined and predictable, such as the unit commitment problem in energy market. Stochastic models are essential when dealing with uncertainty, such as, for instance, renewable energy forecasting or dynamic price fluctuation or demand variations. Choosing between a deterministic and stochastic approach depends on the level of uncertainty in the system and the need for probabilistic risk assessment in decision making. Okay. Thus, we have considered various key aspects of the modeling, of the energy system modeling. Definitely, as you can see, so it's absolutely evident that this is a highly complex process that requires the inclusion of also key constraints. And main of them mentioned here on the slide. The first one is related to the data availability and also the quality. Reliable data is the backbone of the energy model. Models require extensive data sets, and you will see it when you will be implementing your practical task. This includes historical energy consumption, technology performance, economic indicators, environmental factors. Usually, when we are developing a model of any energy system, we are spending a lot of time just preparing the data and making sure that the data available for instance, if we are talking about like a 1 year modeling, so we need to make sure that the data can be found on as a kind of statistical data or the data already published in the transparency platform of NSOE and so on. For instance, if I want to build a model now for the Latvian power system in the SpineOp tool, it 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 could be difficult just because for this particular year we don't have a data yet, and it means that I can do it based on the data available. I can do it for the 2023 maybe, and of course. I will also mention this here that validation is also important for the data as well. So the data gaps, inconsistencies, or outdated information as well can compromise model accuracy and effectiveness. Another one constraint, very important, and once again, I will be repeating uncertainty. Factors like fluctuating energy prices, policy shift, maybe in some cases, technological advancements, climate variability, introduce unpredictability, which we really need to somehow to consider in the energy system modeling. Another one constraint is resolution and computational limit. So I already presented how huge can be a model. If we are, for instance, talking about the MOPA project, so within the project we are developing pan-European energy system, which covers all European countries and covers all main sectors like electricity, gas transport, also heating will be including, and you can imagine the resolution of such model. Another constraint is model calibration, and it's not exactly constraint, but it's maybe the process which results if the model is real. Yeah, this is the model calibration and validation. We have to ensure that the model accurately reflects the real world energy system, and it's the validation and calibration of the model, it's another consuming activity, developing an energy system model. In terms of impact, models must be useful for decision makers. What I want to say here is that we don't need to model for modeling, so we really need uh, to we really need to not exactly to imagine, but to understand the needs of stakeholders who wants to solve a problem, and we really need to address this question through the stakeholder approach. And few more words about additional constraints in optimization modeling. It includes non-linearities, uncertainties, and other complexities. I just want to mention here that there is another one big direction in the energy system, and not only energy system modeling. This is the theory of the constraints, which offers a structured approach how to enhancing the optimization models by identifying and addressing key bottlenecks. So it's continuous process, creating a model, validating the model, and comparing to the real world and so on. So it's a non-stop process. Just to summarize the difference between optimization and simulation models, once again, optimization models are designed to find optimal solution for specific objective, for instance, cost minimization. They are highly efficient for well-defined problems and can handle large-scale system, even under uncertainty. Those models are commonly used for investment planning, dispatch optimization, and infrastructure expansion strategies. However, there is some limitations. Optimization models rely on assumption and simplifications, which may not fully capture the complexity of real-world system. The optimization model effectiveness is highly sensitive to input data and model parameters. Simulation models, on the other hand, are used to analyze dynamic system behavior over the time. They can represent complex interaction, feedback loops, making them particularly useful for the policy impact analysis, behavioral studies, and technological adoption assessment. So it means that new technology inclusion in the generation portfolio of the country. However, simulation models can be computationally intensive, especially when applied to large-scale energy system. Model calibration and validation also can be very challenging to call it simulation model by the end. The choice between those approaches depends on the specific objective of the study, the data available, and the computational resources at hand. With advancement in computing technologies and the evaluating needs of various stakeholders, a wide range of modeling tools have been developed to analyze energy flows, evaluate technology adoption, assess policy impact, and so on. In the following slides, we will introduce key energy system modeling tools and highlight their core functionalities or maybe applications. I will start with the tools for the large-scale power system planning. I also need to mention here or underline that those tools are commercial. but at the same time widely used to optimize operation, expansion, market interaction. For instance, the Plexus tool are used by European Commission, by Joint Research Centers of European Commission, and they very much rely on this tool. If we are going into details, so the Plexus is an advanced energy market simulation and optimization software developed by Energy Exemplar in 1999. It is used for system planning and operational optimization across electricity, gas, and water sectors. One of the Plexus key strengths is its ability to perform both short-term scheduling against such a unit commitment and dispatch, and long-term planning, such as the capacity expansion. It integrates economic and technical factors, including fuel cost, maintenance expenses, emissions, allowing for detailed system analysis. The model implies mixed integer linear programming for optimization, also offering both deterministic and stochastic capabilities. Plexus is capable for high resolution analysis with time step as short as 1 minute. Also, hourly resolution is more common in practice. Like I believe that they are shifting to like a 15 minutes resolution because of the shifting of the electricity market to such time resolution. WASP, so it's a WASP developed by International Atomic Energy Agency, and it first was introduced in 1973. So you can imagine how many times they're already working on the energy planning, energy modeling. It still remains one of the most widely used models for generation expansion planning. Unlike Plexus, which is highly detailed in operation and market simulation, they focus on determining the optimal mix and timing of power plant investment under different scenarios. The model used dynamic programming, which is specifically tailored for the power system expansion modeling. This differs from the standard linear and mixed integer solvers commonly used in energy system models. WASP includes probabilistic estimation of system production cost and outages, making it suitable for long-term strategic planning over several decades. Unlike Plexus, which operates with continuous timelines, WASP typically use annual or seasonal planning periods, grouping demand into typical load blocks instead of hourly or minute-based dispatch modeling. Both WASP and Plexus are commercially available, as I already mentioned, and they are really widely used for the large scale power system models. But as you know, it's not a new approach, but it's already for some times advertising, let's say, by European Commission. And it's also another point that energy system modeling, it's a very complex process, and there is many stakeholders involved, and it's kind of multidisciplinary approach. That's why sometimes it's even easier to use a kind of open approach. And in recent years, has been a growing trend towards openness and transparency in energy modeling. Open source tools and open data contribute to improving scientific quality by enhancing transparency and collaboration. This shift is helping actually researchers, policymakers, and industry professionals develop more accessible energy models. One key initiative in this movement is the Open Mode Energy Modeling Initiative, which fosters the active community, including an online forum where experts discuss methodologies and share some insights, results, some other ideas. And if you are really interested in the energy system modeling, I really to suggest you to join this community. The first open energy system model framework was Balmoral, which was released in 2001. Written in GAMS, Balmoral was designed as a long-term bottom-up energy system model with high flexibility in terms of temporal, sectoral, and geographical resolution. Since then, the open source landscape has expanded significantly. Over the past decades, a range of open source energy system models and frameworks have been developed, including such as the Backbone, also developed by VTT. It's another energy modeling tool, which also can be compared with the SpineOpt, but each of the models have some interesting features. Another maybe Calliope, then Osmosis, Python for power system analysis, OE-MOF, and SpineOpt. Those models serve different purpose, long-term capacity, detailed operation, and just some insights, some details on several of them. Extremely difficult to pronounce, and but Calliope, they call it Calliope, is a multi-scale energy system modeling framework, which is written in Python. It's primarily designed for the energy system planning. Like unlike traditional power system models, this tool does not include power flow analysis, making it more suited for strategic planning than operational dispatch. And of course, it can be like used by the decision makers, like a policy in the policy field. Osmosis, the open source energy modeling system. It is a deterministic linear programming tool designed for the long energy investment planning. It supports generation capacity expansion, provides accessible, compact code-based available in multiple programming languages. Due to its ease of use and adaptability, this tool has been widely adopted in the education, capacity building, stakeholder engagement, just to show them how the energy system modeling can be approached. However, of course, some limitations also need to be mentioned here, such as the low resolution operational problem, or assessing system flexibility issues. The next one is the Python for power system analysis toolbox, probably also very well known, is the powerful open source tools and can simulate optimize electric power system. actually also integrating related energy sectors as well. Unlike the previous frameworks, this tool includes traditional steady-state power flow analysis, enabling multi-period optimization of operation and investment decisions, taking into account transmission network. This makes this tool particularly useful for detailed power system studies that require both and technical feasibility assessment and economic planning. Um, uh, OEMOF Open Energy Modeling Framework is a multi-sectoral energy system modeling tool that employs mixed integer linear programming. It provides a modular and collaborative development framework, making it ideal for the cross-sectoral energy system studies, which I want to highlight today. This is the SpineOpt, or also together with the Spine Toolbox. It's a highly adaptive energy system modeling framework, which is written in Julia, designed for planning and scheduling energy and power system using mixed integer linear programming. What sets SpineOpt apart is its high flexibility in temporal resolution and stochastic structure, allowing user to model different parts of the energy system with varying time horizon and uncertainties consideration and so on. It also supports rolling horizon optimization. If Yeah, so this is SpineOpt. SpineOpt is intended to be used together with the Spine Toolbox, which is an open source software for managing, simulating, and optimizing energy system models. It enables efficient handling of input data, scenarios, and workflow. Mainly it is related to the workflow organization, while also offering also visualization and other functionalities. Additionally, Spine Toolbox facilitates model linking, making it possible to integrate multiple energy system models into a unified workflow. So the more details will be provided today as well about the SpineOpt and a bit of Spine Toolbox. And before we start this, I would like to mention here very briefly about the agent-based modeling. Unlike fundamental optimization model, agent-based modeling captures the real behavior of individual actors in decision making. It allows for the analysis of market effects and design aspects influenced by uncertainty, such as the imperfect information and bidding strategies. However, the number of open source agent-based modeling simulation models remains significantly smaller than energy and power system, like a classical energy system and power classical energy and power system optimization models. But also it need to be mentioned here that as artificial intelligence application advance, agent-based modeling development expected to be expand and which will enhance its role in the energy system analysis as well. As the example of the open agent-based models, I have to mention two of them. The one is a really open access agent-based model, MIRIS, one of the key open source. This is the one probably the one which is open source, designed for the investigation of renewable energy integration in market and market interaction. It enables the study of different market designs, trading strategies, regulatory frameworks in the liberalized electricity market. And another one, an agent-based, let's say this is the framework, so it's not exactly open source, but it's an open access web service for stimulating electricity markets. All the tools I mentioned today, all of them, they have a interesting teaching materials via YouTube channels, via specific web pages, via the community for the energy system modeling. So if you are really interested, you can join. But of course, looking at the at this slide and taking it into account that probably you are more experienced within the electric power system as myself, and the tools which is shown in this slide would be or may be more familiar to you. But it is important to mention here, to note here that over the time, those tools can also be adapted and expanded to model broader energy system as energy sector becomes more integrated. So we are incorporating now electricity, heating, cooling, gas network, and of course the tools must adopt this approach. Okay, this is all from my side. Sorry for my voice. And then, Henrik, I give the floor to you to start the video for the spine opt model. The one is a very short introduction from the web page of the MOPA project, and another one, the more detailed explanation of the spine opt. Thank you very much.
Energy is intangible, yet fundamental to the future of society. The energy landscape is in rapid transition, and it is crucial to keep up with emerging technologies and changing systems. We need tools that can capture the changes whilst enabling cost-effective, sustainable, and reliable energy systems to be planned. To this end, the EU project MOPO is developing state-of-the-art open-source modelling tools. MOPO pulls together existing tools, including Spine Toolbox, Spine Opt, and CoreRes, to allow users to build modelling workflows configured to fit their purposes. MOPO focuses on improving the interoperability, usability, computational efficiency, and visualization capabilities of these tools. The tools will be improved in close collaboration with the end users to ensure their usefulness. The tools will be thoroughly tested and then demonstrated in 2 challenging case studies, one for the whole of Europe and another for detailed modelling of an industrial region. MOPO aims to improve decision-making in the energy domain so that society can achieve environmental and social goals as cost-efficiently and quickly as possible, without risking the reliability and resiliency of the energy system. The green transition in Europe and beyond needs high-quality energy system models. We are ready for the challenge. Are you?
Yeah, so that was the MOPO introduction, and now for the SpineUp video.
Hello. So SpineUp is an advanced open-source energy system modeling framework designed to address the complexities of modern energy systems. Its primary goal is to facilitate both investment and operational planning across integrated energy networks. One of SpineUp's standout features is its flexibility. It allows users to define various temporal scopes for different parts of the model. meaning you can have some input values provided in one resolution while others in a different one. This allows the user to create a model depending on what data they have available or considering the specific modeling needs. Additionally, being overall a generic modeling framework, SpineOpt's adaptability extends to spatial dimensions, enabling the modeling of localized systems like microgrids or expansive national grids, as well as to modeling the functioning of various sectors such as electricity, gas, logistics, and others. In that sense, SpineOpt is a powerful modeling tool that can be adapted to the specific modeling need at hand. The inception of SpineOpt stems from the need to overcome limitations in traditional energy modeling tools. Between 2017 and 2021, the European Union's Horizon 2020 program funded the SPINE project, laying the groundwork for SpineOpt. This initiative emphasized creating open source tools that promote flexibility and integration across various energy sectors. Building upon this foundation, the MOPO project was launched to enhance SpineOpt's capabilities further. The currently ongoing MOPO focuses on developing repeatable and configurable data pipelines, which streamline data management processes and improves the overall user experience, making the tool more accessible to a broader range of users. SpineOpt offers several significant advantages. First, flexibility in modeling. It accommodates complex systems with diverse technologies and interactions, allowing for detailed representations of real-world scenarios. Second, thanks to the adaptable temporal and spatial resolution, the users can customize their models to specific research questions or policy analyses by adjusting temporal, spatial, or even stochastic structures as necessary. Integration across sectors is another strength, wherein SpineOpt enables the modeling of multiple sectors, such as, for instance, electricity, heating, and transport within a single model, facilitating comprehensive analysis of sector coupling strategies. Next, open source and transparent approach promotes collaboration among researchers and industry professionals, fostering continuous improvement and collaborative workflows. Efficient computational performance is another benefit, since SpineOpt is designed for efficiency, thus it can handle large-scale energy systems and scenarios, making it suitable for both academic research and practical applications. And finally, adaptability to policy and market changes, meaning that the framework's flexibility allows its users to quickly adapt to evolving policy frameworks and market conditions, ensuring that analyses can remain relevant in the ever-changing regulatory environments. SpineOpt's unique architecture enables several key features, such as solving the investment matter problem with operational subproblems. This hierarchical structure allows for the simultaneous consideration of long-term investment decisions and short-term operational strategies, ensuring cohesive planning. Then the priorly mentioned flexible temporal and stochastic structures, wherein the framework supports various temporal resolutions and can incorporate stochastic considerations, enabling robust scenario analyses that account for uncertainties in factors like renewable energy production, demand fluctuations, and other non-deterministic factors. And another key quality of SpineOpt is that it can represent different energy carriers, their conversion technologies, as well as energy storage options, providing a holistic view of the energy landscape. At the core of SpineOpt is an objective function designed to minimize total system costs. This comprehensive function includes various cost components which are relevant for the investment planning and/or operational optimization problems. The investment costs are expenses related to building new infrastructure, such as power plants, transmission lines, or storage facilities. Fixed and variable operation and maintenance costs are ongoing expenses required to keep the energy system operational, including routine maintenance and operational activities. Then fuel costs are expenditures on fuel sources necessary for energy production. For combustion units, these are often enough the main cost component, which makes up the marginal cost of a generation unit. Then startup and shutdown costs are associated with initiating or halting the operation of energy units, which can be significant in systems with variable renewable energy sources, forcing thermal units to operate more flexibly. There are a number of other cost components that make up the objective function, but for instance, renewable curtailment costs, which are penalties or costs incurred when renewable energy generation exceeds demand or system capacity, leading to wasted potential, and others, which can be read up more in the online documentation. It is important to note that the objective function as well as the constraints are dynamically formulated during model execution, tailoring to the specific structure and parameters of the model. So, depending on the information provided, SpineUp solves the problem using linear programming or mixed integer linear programming, ensuring computational efficiency and accuracy. In other words, there is a wealth of parameters that can be used to define and construct a SpineUp model, but the user is not required to use all of them, only taking advantage of those which indeed are required for the specific model they are creating and their desired level of detail within it. We will touch on the subject of parameters a moment later. First, let us take a look at how a SpineUp model can be built. The model consists of entities defining the system to be modeled and its structure. There are two groups of entities, zero-dimensional and n-dimensional, each of which have various classes under them. Zero-dimensional entities are the main building blocks of the model, and they usually represent a physical object, whereas multi-dimensional entities generally define the relationships or flows between other objects. So the main or most widely used zero-dimensional classes are connections, which define the means for transfer of commodities between nodes. So these could be transmission lines or pipelines, facilitating the flow of energy across the system. Then we have nodes, which act as aggregators of commodity flows, serving as points where energy is injected, withdrawn, or stored. Examples include geographical regions, specific energy hubs, water reservoirs, and other sorts of objects. And then we have units. These represent energy conversion devices such as power plants. They have the ability to transform one or more commodities, like fuel for instance, into another, like electricity. Of course, there are also entities that are necessary to define the model settings, temporal and stochastic structures, output writing, and similar concepts necessary to adjust how the models are run, but their understanding is best facilitated through hands-on exercises with SpineUp. When it comes to multidimensional entities, which mostly define the relationships of other objects, there is a great number of them possible within SpineUp's framework. So we just give a few examples here. For instance, a three-dimensional connection node-node entity defines that a particular connection is acting over two particular nodes. That is, for instance, an interconnection between two countries. Entities of the unit-to-node class are used to define to which node a unit is outputting a commodity. An obvious example here would be a specific power plant outputting electricity to a specific country node. Altogether, this structured approach allows for detailed modeling of complex energy systems, capturing the interactions between various components effectively. Parameters are used to define the characteristics of the various entities, both zero-dimensional and multi- or n-dimensional, that are used in SpineUp model building. Here is an example of the parameters available for entities of the unit-node class. Overall, they enable defining the objective function coefficients and constraints concerning the flow of a commodity from a specific unit to a specific node, such as capacity, efficiency, ramping constraints, costs, initial state, etc. As you can see from the parameter names in the drop-down menu, notice that there are also parameters available for more advanced modeling needs, such as maximum total cumulated unit flow to node, operating points, and others. There are default values provided for each of the available parameters, which generally are set such so as to not impact your model if you do not require them. Take into account also that each entity class has its own list of available parameters. Moreover, the parameter values can be expressed as fixed values, time series, maps, and other formats, depending on the model data, sophistication, the use case of the particular parameter, and other factors. However, make sure that the specific way of expressing values is meaningful for the specific parameter. Otherwise, you will either get an error at model execution or receive unexpected results. To illustrate the practical application of SpineOpt, let's delve into a straightforward example that demonstrates its modeling capabilities. This example involves a minimalistic energy system comprising two power plants supplying electricity to meet a specific demand. So in this example, we have a fuel node, which serves as the source of fuel for the power plants. Here it is assumed to have an infinite supply capacity, meaning it can provide as much fuel as needed without any limitations. And the other node here is the electricity node, representing the point where electricity is aggregated to meet consumer demand. In other words, this node is where the output from the power plants converges to satisfy the electricity demand requirements. And then we have two power plants represented as units. Power plant A has a maximum capacity of 100 megawatt. It incurs a variable operating cost of 25 euros per unit of fuel consumed and has an efficiency rate of 0.7 megawatt hours of electricity generated per unit of fuel. Power plant B boasts a higher capacity of 200 megawatt. However, it has a higher variable operating cost of 50 euros per unit of fuel, while also having a slightly better efficiency rate, generating 0.8 megawatt hours of electricity per unit of fuel. In this setup, both power plants draw fuel from the fuel node and convert it into electricity, which is then supplied to the electricity node to meet the demand. The system is designed to determine the optimal operation of these plants to minimize total operating costs while satisfying the electricity demand in a single time step. We can infer the single time step to be, of course, 1 hour. In general, this is a very simple optimization problem, the solution to which can easily be obtained even intuitively. But let's try and see how this could be handled formally. By the way, the step-by-step construction of this simple system tutorial within SpineOpt can be studied in the online documentation as one of the first tutorials. So the goal is to minimize the total costs, which, taken into account the input data that we have used, comprises pretty much only the fuel costs associated with each power plant. The objective function in a maximally simplified form then that can be expressed as shown on this slide. So here and here P here denotes power, C is fuel cost, and E is for efficiency. In terms of inequality constraints, we have the flow of electricity from the units being between 0 and the respective maximum capacity, and the equality constraint is the nodal balance in the electricity node, wherein the injection to it from the power plants must be equal to demand. In other words, to the withdrawal from it. By solving this optimization problem, SpineOpt determines that the cost-minimizing solution is to operate power plant A at its full capacity of 100 megawatt in this hour, and power plant B at 50 megawatt. This allocation meets the total demand of 150 megawatt at the lowest possible operational cost. This also makes sense intuitively, as power plant A altogether provides cheaper power, but its capacity is insufficient to meet the whole demand. This example showcases SpineOpt's ability to model and optimize energy systems. Despite its simplicity, the model captures essential aspects of operational planning, including capacity limitations, efficiency rates, and cost minimization. Such foundational models can be expanded to incorporate more complex scenarios, including multiple energy sources, varying demand profiles, and intricate network configurations, demonstrating SpineOpt's flexibility and robustness in energy system modeling. Do note, however, that strictly in SpineOpt terms, the decision variables in this example would be the unit flows, and the specific formulation of the constraints would be in line with the documentation. Specifically, as concerns this simple example, the relevant constraints from the documentation would be node injection, ratios between flows of a unit, and bound on the unit capacity. Here is an example of how a simple system can be expanded to a more complex one. This model represents the finished power system, although objectively still in a fairly simplified manner, since the power generating units are aggregated by type. You either already have or soon enough will encounter this example in the practical lab work. If one was so inclined, the obvious way to further expand this model would be to, for instance, separately model the water flows between hydropower plants, add heating demand nodes to utilize heat energy from cogeneration, or improve the geographic granularity of the transmission network. The wealth of options provided by SpineOpt allows this model to be further developed in a great number of ways. Now, let us pay some attention to the tools that facilitate working with SpineOpt models. Spine Toolbox is an open-source Python package designed to manage data, scenarios, and workflows for modeling and simulation in energy systems. It serves as a centralized platform where users can integrate various data sources, pre-processing tools, models, and post-processing analyses into a cohesive workflow. This integration facilitates seamless data handling and model execution, reducing the complexity often associated with managing multiple tools and datasets. One of the key features of Spine Toolbox is its ability to link data pre- and post-processing tools with multiple models developed in languages such as Python, GAMS, and Julia. This flexibility allows users to incorporate different modeling approaches and tools into their workflows, enhancing the adaptability and robustness of their analyses. Additionally, Spine Toolbox supports parallel execution, enabling users to run multiple models, simulations, or scenarios simultaneously, thereby improving computational efficiency and reducing time required for extensive analyses. This capability is particularly beneficial when dealing with large-scale energy system models that require significant computational resources. The Spine database editor is an integral component of the Spine Toolbox, providing users with the ability to access, edit, and visualize data stored in databases used not just by SpineOpt but other models as well. It offers a user-friendly interface for managing model input and output data, allowing users to inspect and modify model structure, parameters, and results directly within the database. The graphical view, which is shown here, So the graphical views of the example models that I showed priorly are all screenshots from here, from the Spine database editor. This direct interaction with the data enhances transparency and provides greater control over the modeling process. The Spine database editor also facilitates the creation and management of different model configurations by defining scenarios through alternatives. That is, users can set up various scenarios to explore different assumptions, policies, or market conditions, enabling comprehensive sensitivity analysis and robust decision-making support. Under the hood, SpineOpt is implemented in the Julia programming language, known for its high-level syntax and high-performance capabilities, particularly in numerical and scientific computing. Julia combines the ease of use of scripting languages like Python with the execution speed of compiled languages like C or Fortran, making it well-suited for complex mathematical modeling tasks. Within Julia, SpineOpt utilizes JUMP, a domain-specific modeling language for mathematical optimization. JUMP provides a user-friendly interface for defining optimization problems, supporting various problem types, including linear, nonlinear, and mixed integer formulations. This flexibility allows SPINUP to accommodate a wide range of modeling scenarios and complexities. For solving the optimization problems formulated in JUMP, SPINUP integrates with HICE, an open-source optimization solver designed for large-scale linear programming, mixed integer programming, and quadratic programming problems. HICE is implemented in C++ and is known for its efficiency and speed in solving complex optimization problems, making it a suitable choice for the computational demands of energy system modeling. However, in general, SPINUP models can be solved with a number of user-specified solvers, and this specification is done through a parameter within the specific model's database. Currently, HICE is the default solver, though. Now, to conclude our short introduction to SPINUP, let's take note that it and its associated tools are developed and maintained as open-source projects hosted on GitHub, a platform widely used for version control and collaborative software development. Thanks to this, users can report issues, suggest enhancements, participate in discussions, and even contribute code, fostering a collaborative environment. The GitHub repository also serves as a central hub for accessing the latest versions of SPINUP and SPINE Toolbox, along with links to documentation and user guides. These resources provide detailed instructions on installation, usage, and best practices. Thank you for attention. This is it for now.
Okay, so that was the short introduction to SPINUP. And tomorrow and on Friday, we will start the SPINUP project work. So be sure to attend the calculation exercise groups. So tomorrow's group is going to be in A119 and the Friday's group in PB212. And remember, you have to have the, let's see, from our Moodle page, if I can get there. So here you have the required data. So this one. And by the way, there was a question on before. So there were two questions. This asterisk was kind of so we made a correction before this was number 2 and now it's double asterisk. So it's a not Finland between SE2, rather Finland between SE. So you can find that data from Ensoe. And the other question was that then there is the, was it 28th of 3rd, where there's one data point missing in the Excel file. So what you're going to do is you're going to adjust it in a way that you can just delete that row, and then you have 8,760 elements in there. So just delete that row. You had some.
The data has 2 duplicate variables in that. If you delete that, it will be 8,760.
Just make it in a way that you delete that row. So I think Justinas made it in that way. So then you have a similar, if there's an error, you have a similar error in your file. So just delete that empty row in there. So please make sure that you have all of those data files already at hand. And then you have the preparatory session, which is going to be tomorrow and on Friday. You can come with your own computer and you can install this SPINUP and SPINUP toolbox for yourself, but it will be provided in the classroom computers. So this is the one that we are making the session with tomorrow. And seems that Justinas is going to be testing with me right now. So we'll make sure that the computer classes are equipped with the program. Yeah, thank you for this, and I'll be seeing you tomorrow and on Friday.